Hi everyone. In the next couple of videos, we're going to be looking at Chapter 19. And in Chapter 19, we're going to be studying two new tests, the chi-square test for goodness of fit and the chi-square test for independence. And please excuse my voice, I have a really sore throat right now. So in the past, we've looked at a normal distribution, and then we looked at the student T models. Now we're going to look at a third distribution called the chi-square distribution. And we use this distribution when we're doing hypothesis tests for categorical data. Just like the student T models, there are many different chi-square distributions depending on the degrees of freedom. For us, a typical degrees of freedom will be around like 3, 4, or 5. So the shape of the chi-square distribution is going to look like the red one here. I like to call it a ski slope. So there's two things that are characteristics about the chi-square distribution that are important. The first is to notice that the distribution is not symmetric. So unlike the normal model and the student T models, the chi-square distribution is skewed to the right. Also, look at the x-axis. It starts at 0 and goes in the positive direction, which means that the chi-square statistic will always be greater than 0. So we're going to look at an example for the chi-square goodness of fit test. Imagine that a gambler wants to test a die to determine whether it is fair. The roll of the die has 6 possible outcomes, 1, 2, 3, 4, 5, and 6, and the die is fair if each of these outcomes is equally likely. The gambler rolls the die 45 times and counts the number of times each number comes up. The results are presented below. So the first table that you see here are called the observed counts or the observed frequencies. So this is saying that the gambler saw 13 ones, 3 twos, 5 threes, 10 fours, and so on. What we want to do is compare what is observed with what is expected. The expected frequencies are going to be the mean counts that would occur if the null hypothesis were true. In this case, the null hypothesis is that the die is fair, and I'll talk more about hypotheses on the next slide. So if the die is fair, we should see the same number on each number on the die the same number of times. So if we roll the die 45 times, 45 divided by 6 is 7.5. So we should see each number 7.5 times. Now I know that that's not possible, right? We can't observe the roll of a number a half a time. But these are expected values, so you should not round them. Be sure to keep that decimal place. So I have the problem here again, and I've narrowed down the table to show both the observed and the expected. So what we're going to do is run a hypothesis test to determine whether or not what we have observed matches with what we expect. And just to deviate a little bit, I want you to remember that we have natural variation. So, for example, if you were to flip a coin 4 times, theoretically you should get 2 heads and 2 tails. But if you got 3 heads and 1 tail, you probably wouldn't think that there was anything wrong with the coin, because that's just natural variation. The same thing is here, right? We're never going to see a 1 7.5 times, but we want to make sure that what we've observed isn't really far away from what we expect. And so that's what the test is going to test. Okay, so in general, for a chi-square goodness of fit test, the degrees of freedom are the number of categories minus 1. So in this case, we have 6 categories, so the degrees of freedom is 5. In general, for any chi-square goodness of fit test, the null hypothesis is that the distribution of counts fits the stated model, and the alternative hypothesis is that the distribution of counts do not fit the stated model. So in this case, the stated model is that we get each number shows up the same number of times. That's called a uniform distribution. So we would say for the null hypothesis that the distribution of numbers is uniform, and for the alternative hypothesis that it's not uniform. So we have a chi-square goodness of fit test in the calculator, but only if you have a TI-84. If you have a TI-83, you most likely do not have this test programmed into your calculator. So I will show you on the next slide how to do a chi-square goodness of fit test in your calculator. But if you have a TI-84, you probably have this test in your calculator. And it doesn't have to be the newest TI-84. If you have even an older TI-84, this should be there. So we have our hypotheses, our degrees of freedom. What you want to do is put the observed into L1 and the expected into L2. So we're going to go to Stat, Edit, and put the observed into L1 and the expected into L2. And make sure that you have the same number in each list. Then we're going to go to Stat Tests, and we're going to find the chi-square GOF test. And it's way down at the bottom. So scroll all the way down. When you get there, really the only thing you should ever have to change is the degrees of freedom. As long as you always put the observed into L1 and the expected into L2, you really only have to calculate the degrees of freedom and then hit calculate. So we are doing a chi-square GOF test where the observed is L1, the expected is L2, and the degrees of freedom is equal to, again, the number of categories minus 1. So in this case, it's 5. And then hit calculate. And we have a chi-square test statistic of 12.733 and a p-value of 0.026. So just like all the other tests, we have a p-value that is below the significance level, and I believe that was on the other page as 0.1. Either way, even if it's 0.05, it's below. So we write our, I have 0.05 here, so we then write our conclusion in the same way. The p-value is less than our significance level, so we reject the null hypothesis and conclude that there is enough evidence to suggest that the die is not fair. This is a little more complicated with the older calculator. So if you have this test on your calculator, skip over the next slide. You do not have to do anything that I'm doing on the next slide. This is only if you have a TI-83, or if you look and cannot find that GOF test in your calculator. Like if you don't have it, then you should do this. It's going to take a little bit more work with the TI-83, but we're still going to put the observed into L1 and the expected into L2. The chi-square test statistic is found by taking the observed value minus the expected value, squaring it, and then dividing by the expected value, doing that for all of the categories, and then adding up those answers. So we would do 13 minus 7.5, square that, divide by 7.5. We do it again for 3 minus 7.5 squared divided by 7.5. And we do that for all 6 categories, and then we'd add up our answers. You could do this, kind of by hand in that slow way. But you can also have your calculator do most of the calculations for you. So just like we did with the paired t-test, we're going to set L3 to be this inside formula. So our observed is in L1 and the expected is in L2. So if I want to do observed minus expected, I would do L1 minus L2. And then we're going to square it and divide by L2. Then we're going to use a command in your calculator to sum up that whole list of L3. That will be our chi-squared statistic. And then we'll use that chi-squared statistic in the chi-square CDF command. It works a lot like the normal CDF command, except for remember that with chi-square, everything's bigger than 0. So you're always going with your test statistic, or I have like answer, your answer from the other part to positive infinity with your degrees of freedom. Okay, so let's see it on the calculator here. So again, you want to put the observed into L1 and the expected into L2. Then we're going to highlight L3. So I'm going to arrow up to L3 and enter this formula. So I'm going to go up to L3 and add parenthesis L1 minus L2. Close the parenthesis, square it, divided by L2. And then when you hit enter, it will fill in all of those values. Now what's really important is before the next step, you need to go to second, quit, right here. You want to make sure you quit, otherwise it tries to put the sum inside the list, which we don't want. So go to second and quit, so you have like blank screen. And then we're going to go to this stat math, or second stat. So it's under list right here. That's where we're looking for. So we're going to go to second stat, and then we're going to arrow over to math and choose sum. So second stat, arrow over to math, and then sum is number 5. Then you're going to put in L3 and hit enter. That is your chi-square statistic. So from here, we got that the chi-square statistic is 12.733. And this is what we got on the previous page too. Now we want to find the p-value. So we're going to use this chi-square CDF command. That's under distribution like the other CDF commands. But it's number 8. So we're going to put the test statistic that we just found in for the lower bound. You always put the test statistic in the lower bound, and the upper bound is always positive infinity. And then you have to make sure you enter the correct degrees of freedom, in this case 5. And then hit paste. Hit enter, and we have the p-value of 0.026. And then you'd make the same conclusion that we made on the previous page, that it's less than the 0.5, so we reject the null and conclude that there's evidence to suggest that the die is not fair. Okay, let's look at one more goodness of fit test. Oh, assumptions and conditions. I always forget this slide. So the assumptions and the conditions for the chi-square goodness of fit test. You want to make sure that the data that you're using is counted data. So you don't want to be entering in any percents. Everything has to be a count. We have 12 of something or 7 of something. We need an independence assumption. We want to make sure that the counts in each cell are independent of each other. There's not really anything we can do to check this except for look into the scenario of the problem, but for the most part, you need to assume this. And then the last one, when we talk about is the sample big enough, that for a chi-square test is that we want to make sure that the counts in each cell are at least 5. And that's the expected counts. So our expected counts in the last one were 7.5 for everything. So that would be, that would satisfy this condition. So here's another example, and this one has a different type of distribution. So this says a high school principal believes that when the SAT tests are given, the group consists of 10% freshmen, 20% sophomores, 40% juniors, and 30% seniors. The group that just took the test consisted of 12 freshmen, 18 sophomores, 45 juniors, and 25 seniors. So we have what was observed, the counts that were observed, and that's this right here. The 12, 18, 45. So that was observed, and so we have that in our observed list here. The expected, what you want to do is figure out the total number of students. So if we add up what was observed, we see that we have a total of 100 students here. And so we would then, the expected is going to be the counts that follow along with the percents that are given. So I want 10% of 100, or 0.10 times 100 to get 10. So I want 10% of 100 for the freshmen, 20% of 100 for the sophomores, 40% of 100 for the juniors, and 30% of 100 for the seniors. And I want to make sure that what is expected is in counts. Again, we don't want to use the percents. If you add up the expected, you should get the same total as you do for the observed. So we can check our assumptions and conditions. We have that the values in all the cells are counts. It's pretty safe to assume that the counts in each cell are independent. And then the expected counts in every cell are at least 5 or more. So we can state our null and alternative hypothesis. So the null hypothesis, remember, is that what we observe follows the expected distribution. So we would say the distribution of year in high school is consistent with the principal's model, whereas the alternative would be that it's not consistent with the principal's model. We've got 4 categories here, so the degrees of freedom is 3. Okay, so I put both the newer calculator and the older calculator on here, and I'll run both of them. So the newer calculator, you guys have it a lot easier here, but for both of you, you're going to put the observed into L1 and the expected counts into L2. For the newer calculator, once you have that data in for your observed and expected, you're going to go to Stat, Tests, and go all the way down to the GOF test. Don't forget to make sure that your degrees of freedom is changed and calculate. And you'll get a test statistic of 2.058 with a p-value of 0.56. It's a really high p-value. All right, let's do the same one with the older calculator because we have a lot more steps with the older one. But you're still going to put your observed into L1 and your expected into L2. And now we're going to put that formula in for L3. So make sure to arrow up. It's L1 minus L2 squared divided by L2. and then hit enter. From here, we want to sum L3, right? We want to add up all of these answers. So we're going to do second stat. We're going to go to that list and arrow over to math. So second, oh, don't forget to quit. I always forget to quit. Second stat, arrow over to math, and it's number 5. You're going to sum list 3, and that gives you that test statistic of 2.058. Put that into the chi-square CDF command, and it's always your lower bound. Don't forget to change your degrees of freedom. And then we get the same p-value, 0.56. So we can state the same conclusion with these, which is that since the p-value is greater than the 0.01 or 0.10, we fail to reject the null hypothesis and conclude that there's not enough evidence to suggest that the distribution is not as the principal believes. So there's a lot of nots in there, right? But we don't have enough evidence to support the alternative hypothesis, which is that the distribution is not as the principal believes. Right? So I'm not saying the null is true. I'm saying I don't have enough evidence to suggest that the alternative is true. It's kind of weird, but it's a little weird in this scenario. All right, so I'm going to end this video here, and we're going to do the chi-square test for independence in the next video.